Alright, once again, here we are in parallel circuits. This will be the last one on our parallel circuits. We have already covered parallel circuit calculations and parallel circuit faults for opens and shorts. In this video, we are going to look at parallel circuit faults for changed values. And so changed value is just a resistor or any load device that has increased or decreased out of its ohmic value tolerance. In this particular example, we're going to use R1, and it had an original value of 10k ohms, you can see on the screen. And that is going to have decreased out of tolerance to 5k ohms. With this change in resistance, we are going to see a change in total resistance and a change in total current. So let's look first at total resistance. Originally, we know we had a value of 2.86k ohms. Now, when we look at our new values, we actually see a decrease in resistance to 2.22k ohms, which makes sense because one of our branches decreased in value, so we see a total decrease in our resistive value. So now again, it's a good opportunity to look at our Ohm's law arrow theory, and if we put our circuit up on the board, we have voltage is equal to current times resistance. We put in the arrows for the values that we know, so we know that resistance is going down and voltage is staying the same. So based on those arrows, we know to balance out the equation, current must be going up. So let's go ahead and look at what's going on with current. We look at branch 1, and we did originally have 100 volts divided by 10k, which gave us 10 milliamps. But now, of course, we have 100 volts divided by 5k ohms, which will give us a new branch current of 20 milliamps. And we do the same thing. We look again at branch 2, but we know the values in branch 2, 100 volts divided by 5k ohms, has not changed, and so we still have 20 milliamps in branch 2. And again, we look at branch 3, we have the same 100 volts divided by the same 20k ohms, and again, we do not see a change, so it has the same 5 milliamps of current. Now we look at total current. That was our original total current with our 10 milliamps or 20 milliamps and our 5 milliamps equaling 35 milliamps. Well, now of course we have a much larger current through branch 1 because we know that current and resistance are inversely proportional. So when resistance in the branch went down, current in the branch went up, which makes our total current, of course, much higher. It's 45 milliamps now, which is 20 milli plus 20 milli plus 5 milli. And of course you can see exactly the same thing if you put it through Ohm's law, which is the voltage divided by resistance. If I take my voltage of 100 volts divided by my new smaller resistive value of 2.22k, I see a total current that is 45 milliamps, the same as if I added them together, and it is indeed much larger than it originally was. So it shows us that our Ohm's law arrow theory works without doing any of the numbers. Now we take one last look at voltage, and we see that even though the ohmic value of the branch has moved, it has changed for branch 1, it is no longer 10k ohms and now 5k ohms, it does not change the voltage that we see to that branch because, of course, we understand that when we read voltage in a parallel circuit, we are essentially just reading across our battery by putting our black lead down on our negative side and our red lead up on our positive side. We read across that voltage source no matter where we are within the circuit, as long as we have the black lead below the voltage source or any of the resistors and the red lead above the voltage source or any of those resistors. So we see that there is no change in the voltage for those branches. They all still see the 100 volts applied. Alright, and that is change values in a parallel circuit. We are going to move on to series parallel circuit calculations next.